Our solar system has a glaring gap where a planet should be. For centuries, astronomers have chased the ghost of a missing world, a lost piece of our cosmic family portrait. This is the story of that hunt, a journey through mathematical predictions, mistaken identities, and stunning discoveries that will change how you see our celestial neighborhood. By the end, you will understand the compelling evidence for a hidden giant still lurking in the dark and the cataclysmic collision that might explain our own moon. Were the asteroids once a planet, and could a black hole be hiding beyond Pluto? The search for answers reveals just how dynamic and unfinished our solar system's story truly is. What does the idea of a lost world make you wonder about our place in the cosmos? That gap in the solar system was not just a feeling, it was a number. In the 1770s, a pattern emerged so strange it felt like a cosmic secret. A German astronomer named Johann Titius noticed something peculiar about the distances of the planets from the Sun. He saw a mathematical sequence take the numbers 0, 3, 6, 12, 24, 48, and 96. Each number is double the one before it, starting after 3. Now add 4 to each of them. You get 4, 7, 10, 16, 28, 52, and 100. Divide those by 10, and you have the approximate distances of the known planets from the Sun, measured in astronomical units. One astronomical unit is the Earth-Sun distance. Mercury is about 0.4, Venus is 0.7, Earth is 1.0, Mars is 1.6, then came the gap. The sequence predicted a planet at 2.8 astronomical units, but there was nothing there, just empty space. Then Jupiter fit perfectly at 5.2 and Saturn at 10.0. This pattern became known as the Titius-Bode law. For decades, it was a curious footnote. Then, in 1781, William Herschel pointed his telescope and found a new planet, Uranus. Its distance from the Sun, 19.2 astronomical units. The law predicted 19.6. It was astonishingly close. Suddenly, this mathematical rule was not just a coincidence, it was a predictor. And its prediction of a world at 2.8 astronomical units now screamed for attention. The empty space between Mars and Jupiter was not just empty, it was mathematically wrong. Science now had a target, a specific address in the sky where a planet ought to be. This was the spark that ignited the first great organized hunt for a missing world. Astronomers across Europe began to scan the heavens, convinced they were not just searching for a rock, but for a piece of a hidden cosmic order. The hunt was on, and it would lead to a discovery no one expected. Armed with a mathematical prediction, the astronomical community mobilized. This was not a casual glance through a telescope, it was a coordinated manhunt for a missing world. The idea was so compelling that in the year 1800, a group of 24 of Europe's leading astronomers formed a secret society. They called themselves the Celestial Police, and their mission was clear: to patrol the zodiac, the band of sky where the planets travel, and find the fugitive planet at 2.8 astronomical units. They divided the sky into 24 zones, one for each member to meticulously sweep with their telescopes night after night. The coordinator of this grand operation was a German-Hungarian astronomer named Baron Franz Xaver von Zach. He was the perfect commander, a brilliant organizer with connections across the scientific world. Under his direction, the hunt became systematic, a grid search of the cosmos. Imagine the anticipation, the nightly routine of peering into the eyepiece, charting faint stars, hoping one of them would move. The competition was fierce but collaborative, a shared dream of cosmic completion. Every observatory in Europe was on alert, each clear night holding the potential for immortal discovery. The tension built for months. Then, on the first night of the new century, January 1st, 1801, the news came. But it did not come from a member of the Celestial Police. It came from an astronomer working alone in Sicily, Giuseppe Piazzi, who was not even looking for a planet. He was creating a star catalog. On that historic night, he noticed a faint star-like object in the constellation Taurus. He observed it again the next night, and it had moved. He wrote to his colleagues with cautious excitement, believing he had found a new comet. As word spread to Baron von Zach and the Celestial Police, the excitement turned to frenzy. They began tracking it, calculating its path. This was no comet. Its orbit was nearly circular, and it lay precisely where the Titius-Bode law predicted, at 2.8 astronomical units from the Sun. They had found it, or so they believed. The lost planet was real, and they named it Ceres after the Roman goddess of agriculture. The mystery of the gap was solved. But the celebration was short-lived, because what they found was not a world anyone had imagined. Giuseppe Piazzi's discovery sent a wave of triumph across Europe. The lost planet had been found, and it was named Ceres. For a brief, glorious year, astronomy textbooks were rewritten. The solar system was whole again, the mathematical prophecy fulfilled. But that sense of completion began to fracture almost immediately. As astronomers trained their telescopes on this new world, a problem emerged. Ceres was frustratingly faint, a mere pinprick of light with no discernible disk. Even through the most powerful telescopes of the era, it refused to resolve into a proper globe. This was not the silhouette of a major planet. The excitement curdled into a profound confusion. What exactly had they found? The answer arrived with devastating swiftness. Just over a year later, in 1802, another astronomer found a second object in nearly the same orbit. They named it Pallas, then came Juno, then Vesta. Within a decade, the tidy story of a single missing planet had completely shattered. The gap between Mars and Jupiter was not occupied by one world, but by a swarm of them. Ceres was not a planet. It was simply the largest member of a vast, fragmented community. The grand hunt had succeeded in finding something, but it had failed to find what it was looking for. The mathematical law had pointed to an address, but the cosmic reality was an entire neighborhood. This forced a monumental shift in human understanding. The asteroid belt, as this region came to be known, was not a failed planet but a fundamental feature of our solar system. For centuries, Ceres itself occupied a strange limbo, too significant to ignore yet too small to fit the old categories. It was only in the 21st century, with new definitions, that it found its rightful place as a dwarf planet, a king of the asteroids. The discovery of Ceres was a moment of brilliant success that immediately revealed a deeper, more complex truth. The universe does not always conform to our neat patterns. Sometimes, the answer to a simple question opens a door to a room we never knew existed, and in that room, the real mystery was just beginning. What could have prevented a full-sized planet from forming in that space, leaving only these broken pieces behind? The asteroid belt we imagine is a Hollywood fantasy. We picture a dense, swirling field of tumbling rocks where spacecraft must dodge and weave for survival. The reality is profoundly different and far more telling. This vast region between Mars and Jupiter is mostly empty space. If you were to stand on an average asteroid, your nearest neighbor would likely be millions of miles away, a lonely speck in a profound darkness. The combined mass of every single rock, boulder, and dwarf planet in the entire belt amounts to less than 4% of our moon's mass. This is not the stuff of a shattered planet. It is a sparse collection of leftovers, a clue written in fragments. The four largest members dominate this realm: Ceres, a spherical dwarf planet with a mysterious, briny ocean hidden beneath its dusty crust; Vesta, a battered protoplanet with a colossal impact basin so deep it exposes the mantle below; Pallas, a tumbling, cratered world with a wildly tilted orbit; and Hygeia, nearly spherical itself, possibly reshaped by a giant collision. These are not just rocks. They are the survivors, the almost planets that grew up in a very tough neighborhood. So why is the belt so sparse? The leading theory points a gravitational finger at the solar system's giant, Jupiter. As the young gas giant formed, its immense gravity began to act like a cosmic wrecking ball in the nearby construction zone. It stirred up the primordial material between Mars and itself, accelerating the pebbles and planetesimals. Instead of gently coalescing into a new world, these building blocks were thrown into chaotic, high-speed orbits. When they collided, they shattered rather than stuck together. Jupiter's relentless tug essentially starved the region, preventing a planet from ever accreting. The asteroid belt is not a graveyard, but a construction site that was permanently shut down. Yet there is another, more violent possibility whispering from the fragments. Could this be the debris of a catastrophic planetary collision? Some models suggest that in the solar system's violent youth, dozens of Mars-sized protoplanets jostled for position. A direct hit between two such bodies would have been apocalyptic, scattering their remains across an orbital highway. The varying compositions of asteroids, from metallic to rocky to carbon-rich, could hint at the layered guts of differentiated worlds torn apart. This idea transforms the belt from a failed project into a cosmic crime scene. Is it a collection of unfinished building blocks, or the scattered remains of a murdered world? The answer may be both. The truth likely lies in a story of gravitational disruption punctuated by epic violence. Jupiter prevented a planet from growing, but it may have also orchestrated the collisions that shattered the next best things. The asteroid belt is our solar system's attic, storing the leftover materials and broken toys from its earliest days. To sift through its rubble is to read the opening chapters of our planetary story, written not in words, but in orbits and impact scars. And if this region holds such a turbulent past, what other forgotten cataclysms might have shaped our familiar cosmic neighborhood? The asteroid belt tells a story of a world that never was, but what about a planet that was seen, studied, and then vanished from the maps entirely? In the 19th century, the solar system seemed to hold another ghost, one orbiting closer to the sun than any other. This was Vulcan, a world born not from a gap in a pattern, but from a wobble. The planet Mercury has a peculiar orbit. Its elliptical path around the sun itself rotates very slowly over time, a phenomenon called the precession of its perihelion. Newtonian physics could explain most of this motion, but not all of it. A tiny, stubborn fraction of that rotation was unaccounted for, an anomaly that gnawed at the greatest mathematical minds of the age. Into this puzzle stepped Urbain Le Verrier, the French astronomer who had famously used similar calculations to predict the existence of Neptune. If the math had worked for the outer solar system, why not for the inner? Le Verrier became convinced that the only explanation for Mercury's errant wobble was the gravitational pull of an unseen planet, or perhaps a band of small bodies orbiting between Mercury and the Sun. He calculated its probable mass and orbit, and in 1859 he announced the discovery of the planet Vulcan, sight unseen. The scientific world erupted. Here was a prediction from a proven master, and astronomers scrambled to find this scorched inner world. The challenge was immense. Observing anything so close to the sun's blinding glare was perilous, limited to brief moments during solar eclipses or the rare transit when the object might pass across the solar disk. Yet reports began to trickle in. An amateur astronomer named Edmond Lescarbault claimed a definitive sighting, a small, round dot moving across the face of the sun. Le Verrier, overjoyed, verified the report, and Vulcan was officially added to charts and textbooks. For decades it was taught as fact, but Vulcan was a phantom. Other astronomers failed to confirm the sightings. The purported observations were inconsistent, often explained by sunspots or simple human error. The planet that had to exist according to the impeccable math simply was not there. The mystery of Mercury's orbit persisted, a tiny but profound flaw in the universe's clockwork. The solution arrived not with a bigger telescope, but with a revolutionary new theory of gravity itself. In 1915, Albert Einstein published his theory of general relativity. It proposed that gravity is not a force acting across space, but the curvature of spacetime by mass. When Einstein applied his equations to Mercury's orbit, the extra precession calculated out perfectly. The Sun's immense mass warps the space around it, and Mercury, moving so close, must travel along that curved geometry. The anomaly was not caused by a hidden planet, but by the very nature of space and time. Vulcan was erased, but its legacy was profound. The decades-long search for a planet that did not exist had helped expose a fundamental limitation in Newtonian physics. It was a scientific error that, by persisting, pointed the way to a greater truth. The story of Vulcan is a humbling reminder that sometimes the universe's most compelling clues are not hidden objects, but tiny imperfections in our understanding of reality. The ghost of Vulcan had been banished by a new theory of gravity, but the power of prediction was not finished with our solar system. It would soon turn its gaze outward, beyond the last known planets, into a cold and dark frontier where mathematics once again insisted something was missing. The stage for this new mystery was set by a stunning success. In the 1840s, astronomers were puzzled by irregularities in the orbit of Uranus, the planet discovered by Herschel. Its path deviated slightly from Newtonian predictions, as if an unseen hand was giving it a gentle, persistent tug. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated the position of a hypothetical eighth planet that could explain these wobbles. When Le Verrier sent his coordinates to the Berlin Observatory in 1846, Johann Gottfried Galle pointed his telescope and found Neptune within 1 degree of the predicted spot. It was a triumph of celestial mechanics, proof that the universe could be decoded with pen and paper, but the story did not end there. Once Neptune was found and its mass calculated, astronomers expected the solar system's balance sheet to be settled. It was not. Tiny, stubborn discrepancies remained in the orbits of both Uranus and now Neptune itself. The gravitational ledger still did not add up. Into this accounting error stepped a wealthy, determined, and controversial American astronomer, Percival Lowell. Convinced the anomalies pointed to a ninth planet, he dubbed it Planet X. Lowell built his own observatory in the clear skies of Flagstaff, Arizona, specifically for this hunt. For years, until his death in 1916, he and his team meticulously photographed sections of the night sky, comparing glass plate photographs taken nights apart, searching for one faint dot that had shifted against the backdrop of fixed stars. It was grueling, eye-straining work. Lowell filled notebooks with complex orbital calculations, mapping the probable path of his phantom world. He was driven, some said obsessed, by a desire for a discovery that would crown his legacy. The search for Planet X captured the public imagination, becoming a staple of newspaper headlines and popular science. It was a real-world detective story, a scientific quest for a hidden giant in our own cosmic backyard. Lowell never found his planet, but the seed he planted, the idea of a massive, unseen perturber in the outer dark, would not die. It lay dormant for years, waiting for a new generation of technology and a fresh pair of eyes to rekindle the hunt, a hunt that would lead to a discovery far stranger than anyone could have predicted. The search for Planet X did not end with Percival Lowell's death. It became his legacy, a challenge left to the observatory he built. A young farm boy from Kansas, Clyde Tombaugh, arrived at the Lowell Observatory in 1929 with a talent for meticulous observation and a relentless patience. His task was monumental: to resume the photographic hunt for Lowell's phantom whirled across the vast, star-strewn plain of the ecliptic. Night after clear, frigid Arizona night, he operated the observatory's astrograph, capturing glass plates of the same star field on different evenings. Then came the painstaking part. He used a device called a blink comparator, a machine that allowed him to rapidly switch his view between two plates. Stars would remain fixed, but any object that had moved its position, a planet, asteroid, or comet, would appear to jump back and forth. It was like watching the cosmos blink. For months he examined hundreds of thousands of pinpricks of light, his eyes straining for that telltale hop. Then, on February 18, 1930, after comparing plates taken in late January, he saw it. A faint 15th magnitude dot had shifted position in the constellation Gemini. He checked again, his heart pounding. He brought in the observatory director, who confirmed the find. After a tense period of verification, the announcement electrified the world on March 13, 1930. The headlines declared the discovery of Planet X, the ninth planet, found exactly where Lowell's calculations had suggested. They named it Pluto for the Roman god of the underworld, a fittingly dark and distant ruler, and its first two letters secretly honored Percival Lowell. The solar system, it seemed, was complete at last, but almost immediately Pluto began to act strangely. As decades passed and technology improved, astronomers realized this was no gas giant like Neptune. Pluto was shockingly small, smaller than our own moon. Its orbit was wildly eccentric and tilted far out of the plane of the other planets, crossing inside Neptune's path for 20 years of its 248-year journey. Then, in 1978, astronomers discovered it had a massive moon, Charon, so large relative to Pluto that the two essentially orbit a point between them, like a pair of icy dancers holding hands. Pluto was not the massive gravitational bully perturbing the giants. It was a tiny, frozen oddball. The mystery of the orbital anomalies that had sparked its search remained unsolved, and a new, more profound question took its place. If this was Planet X, what exactly had we found? The discovery meant to solve a puzzle had instead opened a cosmic identity crisis. What, in the end, makes a planet a planet? Pluto's reign as the ninth planet was a fragile one, built on a misunderstanding of its own size and power. For decades, it was the solar system's peculiar outcast, a frozen oddball in the textbooks, but still a planet. That status began to crumble in the 1990s, not from a single blow, but from a cascade of discoveries that revealed Pluto was not alone at the edge of darkness. Astronomers had long theorized about a vast reservoir of icy bodies beyond Neptune, a relic of the solar system's formation called the Kuiper Belt. As telescopes grew more powerful, they began to find them first by the dozens, then by the hundreds. Pluto, it turned out, was not a solitary wanderer. It was simply the first and brightest member of this immense frozen swarm. The final challenge to its title arrived in 2005. A team led by astronomer Mike Brown discovered an object even more distant than Pluto, and preliminary observations suggested it was also larger. They named it Eris, after the Greek goddess of discord, a fitting name for the celestial body that would ignite a planetary war. Here was the crux of the crisis. If Pluto was a planet, then surely Eris, a rival in size and orbit, must be one too. And what about the other large Kuiper Belt objects being found, like the egg-shaped Haumea with its bizarre spin, or the reddish Makemake? Did we suddenly have 13 or 30 or 300 planets? The International Astronomical Union, the body responsible for celestial nomenclature, faced a profound and messy decision. In 2006, at a now infamous meeting in Prague, they voted to establish a new definition. A planet, they declared, must orbit the Sun, be massive enough to be rounded by its own gravity, and crucially, must have cleared its orbital neighborhood of other significant debris. Pluto failed this third test spectacularly. It shares its cosmic highway with countless other Kuiper Belt objects, and so, with a vote that felt to many like a demotion, Pluto was reclassified as a dwarf planet, a new category for those round worlds that do not dominate their orbits. The public reaction was one of surprising heartbreak and outrage. For generations, Pluto had been a fixture, a friendly underdog at the edge of every classroom mobile. Its loss felt personal, a shrinking of our cosmic family, but scientifically the debate was clarifying. It forced us to ask what a planet truly is, not as a sentimental label, but as a dynamical class of object. The solar system was not losing a planet, It was gaining an entirely new understanding of its architecture, and this resolution exposed the original mystery all over again, now sharper than ever. Pluto was never the massive planet X that Percival Lowell sought. Its gravitational influence was negligible, so if a small, icy dwarf planet was not the source of those lingering orbital tugs on Uranus and Neptune, then what was? The hunt for the real perturbing force, for a true hidden giant, was back on. The demotion of Pluto was not an ending. It was the opening of a far stranger and more compelling chapter. Pluto's demotion did not close the book on the outer solar system. It tore out the final page and revealed a hidden appendix. The Kuiper belt was not just a collection of icy leftovers. It was a message, and a small group of extreme objects were spelling out a warning in their impossible orbits. Far beyond Neptune, out where the sun is a mere bright star, a handful of frozen worlds behave as if they are not truly free. Their elongated paths are strangely tilted, and most tellingly, they cluster together, their points of closest approach to the sun all bunched up in one region of space. Statistically, this clustering is like finding a dozen scattered compass needles, all pointing in the same direction by pure chance. It should not happen. Something, astronomers realized, must be hurting them. This is where the modern hunt for a true hidden giant begins, not with a blurry photograph, but with a brilliant piece of gravitational detective work. In 2016, astronomers Konstantin Batygin and Mike Brown, the same Mike Brown who discovered Eris, published a blockbuster analysis. They ran countless computer simulations of the outer solar system, and the only way to recreate the bizarre orbital clustering they observed was to introduce a new, massive planet. This hypothetical world, which they call Planet 9, is not a small ice dwarf. It is a monster, a super-Earth or a mini-Neptune with a mass 5 to 10 times that of our own planet. Its proposed orbit is staggering. It would swing from a closest approach perhaps 300 astronomical units from the Sun, out to an aphelion of 600 or 700 astronomical units, completing a single, lonely circuit around the Sun every 10,000 to 20,000 years. Picture this in your mind, an Earth-like world, but many times more massive, moving through a perpetual twilight so far away that our sun would appear only as a particularly intense star in its black sky. Its gravitational influence is not a direct visible tug on the giant planets anymore, but a subtle, long-term sculpting force on these smaller, distant bodies, aligning their orbits like a hidden conductor guiding an orchestra no one can see. Animated simulations of this are mesmerizing. You see the scattered dots of the extreme trans-neptunian objects moving in their wild ellipses, and then you introduce Planet 9 into the model. Slowly, over millions of simulated years, its persistent gravity gathers those chaotic orbits, shepherding their closest approaches into that telltale cluster and tilting their paths in unison. It is a compelling, elegant solution to a deep orbital mystery. The evidence is not a photograph, but a pattern, a signature written in the frozen paths of the solar system's most distant inhabitants. The case for Planet 9 is built on the pure, predictive power of celestial mechanics, a ghost inferred from the disturbed motions of other ghosts. If it is real, our solar system is not the tidy 8-planet system we know. It harbors a colossal, alien world in its profound outer dark, a relic from the dawn of planetary formation that was flung outward and now watches from an unimaginable distance. The question now shifts from if it exists to how we might finally catch a glimpse of it. The evidence for this hidden giant is written in the ice. To understand it, we must meet the messengers, a handful of frozen worlds so distant and strange they seem to defy the solar system itself. The first and most famous of these is Sedna. Discovered in 2003, Sedna is an enigma wrapped in a deep red hue. Its orbit is staggering. At its closest approach, it comes no nearer than about 76 astronomical units from the Sun, more than twice as far as Neptune. Then it swings out on an elongated 12,000-year journey to a mind-bending distance of over 900 astronomical units. To put that in perspective, from Sedna at its farthest, the Sun would be a pinpoint of light, barely distinguishable from the brightest stars. Sedna is utterly detached from the gravitational influence of the giant planets, a lonely wanderer in a realm of perpetual twilight. Its existence alone was a puzzle. How did it get there? It is too far out to have been scattered by Neptune, and not far enough to have been captured from interstellar space. Sedna seemed like a cosmic orphan. Then came another, designated 2012 VP113, nicknamed Biden for its catalog code. Its orbit is similarly extreme, never coming closer than 80 astronomical units. The discovery of these and a few other objects revealed a pattern that was impossible to ignore. These extreme trans-neptunian objects do not have random orientations. Their elliptical orbits are aligned, all pointing in roughly the same direction in space. Even more telling, the points where they make their closest approach to the Sun, their perihelia, are not scattered around the solar system. They are clustered together, as if an invisible fence is holding them in one quadrant of the sky. Think of it like this. Imagine you have a dozen comets with wildly different, elongated orbits around the Sun. By pure chance, you would expect their closest points to the Sun to be randomly dotted all around the solar circle, but instead, you find them all huddled together in one arc, like sheep kept in a pen. The statistical odds of this happening naturally are astronomically low, less than 1%. Something must be organizing them, herding their orbits into this peculiar configuration. This is the gravitational signature of Planet 9. In simulations, a massive planet on a tilted, distant orbit acts like a slow-moving shepherd. Over millions of years, its persistent tug torques the orbits of these smaller bodies. It pushes their perihelia away from its own path, effectively gathering them into that observed cluster, and it forces their orbital planes to line up with its own. The dance of these frozen worlds is not chaotic. It is choreographed by a master we have yet to see. Each of these distant ice balls, from the reddish Sedna to the more recently discovered 2015 BP 519, is like a single compass needle. Alone, it points nowhere, but when you see half a dozen of them all pointing in the same direction, you have to conclude there is a powerful magnet somewhere in the dark. They are not proof, but they are a trail of breadcrumbs leading us into the solar system's deepest shadows. So, what is this hidden shepherd, if it truly exists? The nature of Planet 9 is a theoretical playground, a puzzle where each possible answer paints a dramatically different picture of our solar system's history. One compelling idea is that it is a captured exoplanet, a rogue world born around another star. In the solar system's infancy, our Sun was part of a dense stellar nursery, with other newborn stars passing relatively close by. During this chaotic dance, the gravitational pull of our young Sun could have snatched a free floating planet or stolen one from a neighboring star's outer disk. If true, Planet 9 would be an interstellar immigrant, a permanent visitor from another cosmic family, carrying with it the chemical signature of a different birthplace. Its orbit, so distant and tilted, would be the frozen record of that ancient theft. Another possibility is that it is a native giant, but one that suffered a violent exile. Early planetary formation was a game of gravitational pinball. Models suggest our system may have originally contained a fifth giant planet, perhaps an ice giant like Uranus or Neptune. A close encounter with Jupiter could have flung this world outward on a trajectory so extreme it never returned, becoming a permanent outcast in the frozen fringes. In this scenario, Planet 9 is not an alien, but a long-lost sibling, a prodigal giant whose core might be surrounded by a thin, frozen atmosphere, a ghost of its former self. Perhaps the most intriguing theory is that it is a super-Earth, a type of planet common throughout the galaxy, but conspicuously absent from our own solar system. These are rocky worlds several times more massive than Earth, often with thick atmospheres. Our planetary formation process somehow skipped this step, or perhaps it did not. Planet 9 could be that missing link, a primordial super-Earth core that formed quickly in the outer disk before the sun's radiation blew away the gas, leaving behind a massive, icy, rocky world. It would be a relic of a road not taken, a glimpse at what our neighborhood might have been like under different circumstances. Detecting such a world, however, is a monumental challenge. At its proposed distance, the Sun is 1,000 times fainter than it is at Pluto. The world would be bitterly cold, barely reflecting any sunlight, a dark silhouette against a slightly darker sky. Our best hope lies in its faint, lingering heat signature. Every object with mass glows with a tiny amount of thermal radiation. Powerful telescopes like the Subaru telescope in Hawaii and the Vera Sea. Rubin Observatory in Chile are conducting deep, systematic surveys of the predicted sky region, not looking for a glint of sunlight, but for the slow, creeping motion of a single, faint infrared dot against the fixed stars. It is a search for a cosmic ember in an ocean of black. Artist concepts of Planet 9 try to bridge this gap between theory and observation. Some depict it as a dark, blue-hued ice giant, streaked with the frozen remnants of a hydrogen atmosphere. Others imagine a super-Earth, a rocky world with a global, frozen ocean under a deep, starry sky, its surface etched by eons of cryovolcanic flows. These images are not evidence, but they are vital tools for the imagination, helping us visualize the profound loneliness of a world that may have spent the entire history of human civilization completing just a fraction of its orbit. The search continues, a patient scan of the void for a gravitational ghost that may forever redefine our place in the cosmos. The search for this gravitational ghost is a race against darkness and distance. Astronomers are not simply pointing telescopes at random. They are conducting the most meticulous sky census in history, armed with instruments of breathtaking sensitivity. The primary tool in this hunt is the Subaru telescope, perched atop Mauna Kea in Hawaii. Its massive mirror, over 8 meters across, gathers faint light like a cosmic bucket, and its hyper-suprime cam is a digital eye with a field of view so wide it can capture the equivalent of several full moons in a single exposure. Night after night, it scans the predicted orbital path of Planet 9, capturing images of the same patch of sky weeks or months apart. The goal is not to see the planet directly in one image, but to detect its motion. A distant planet moves imperceptibly slowly against the backdrop of infinitely distant stars. By comparing these digital snapshots over time, sophisticated software flags any dot that has shifted position. It is a process of digital subtraction on a galactic scale. Another critical player is the Pan-STARRS system, also in Hawaii, which continuously scans the entire visible sky to create a living map of millions of celestial objects. Its vast archive is a treasure trove for hunters, allowing them to check if any faint, moving object was spotted years ago and then lost. The real game changer, however, is waiting in the wings. The Vera Sea Rubin Observatory, currently under construction in Chile, will soon unleash an unprecedented view. Its 8.4-meter mirror and a camera the size of a small car will photograph the entire southern sky every few nights for a decade. This legacy survey of space and time will not just look for Planet 9. It will create a high-definition, time-lapse movie of the universe, catching any slow-moving object in its net. The process is brutally painstaking. Each night's data contains billions of pixels, each representing a point of light. Algorithms sift through this ocean of data, filtering out known asteroids, distant galaxies, and cosmic ray strikes. What remains is a short list of candidates, perhaps a handful of suspicious dots that move just a fraction of a pixel between observations. Each candidate must then be verified, its motion tracked over subsequent nights to confirm it follows a slow, steady path consistent with a distant orbit. It is the ultimate needle in a haystack search, where the haystack is the entire sky and the needle is a speck of charcoal lost in the dark. The public often sees beautiful colorized images from these surveys, vast star fields streaked with the trails of asteroids. But the raw data for the Planet 9 hunt looks different. It is often a pair of grainy black and white images side by side, with a single circled dot that has jumped position. That tiny hop, that almost imperceptible shift, could be the first glimpse of a world larger than our own, hiding in plain sight for billions of years. The hunt is a testament to patience, a slow, deliberate sweep of the cosmic frontier, where every clear night holds the potential to rewrite our solar system's family portrait. Yet for every compelling signature, science demands a skeptic. The case for Planet 9 is powerful, but it is built on inference, not observation, and in that gap, alternative explanations bloom. Could the orbital clustering be an illusion, a trick of the light and our own limited perspective? The most straightforward challenge is observational bias. The extreme trans-neptunian objects we have found are incredibly faint, detectable only in tiny, specific patches of sky where our most powerful surveys have pointed. What if, by sheer chance, our deepest searches have only been conducted in the direction where these objects happen to be clustered? It is like searching for mushrooms in a forest, but only looking under oak trees, then concluding all mushrooms grow under oaks. Until we have a complete, uniform map of the entire distant sky, we cannot rule out that the pattern is a statistical fluke, a cosmic coincidence born of where we have chosen to look. New, wider surveys like the one planned by the Vera C. Rubin Observatory will be the ultimate test, scanning the entire sky to see if the clustering holds or dissolves into randomness. A more physical alternative points not to a single giant, but to a crowd of small ones. Could the gravitational shepherd be not a planet, but a vast primordial disk of icy debris? Early in the solar system's history, a massive ring of small bodies may have existed far beyond Neptune. The collective gravity of this disk, acting over billions of years, could have gently torqued the orbits of objects like Sedna, herding them into the observed alignment. In this model, Planet 9 is replaced by the ghost of a structure, the fading gravitational memory of a disk that has since dissipated or been stripped away. It is a subtler explanation, one that requires no new, unseen world, only the lingering influence of the ancient building blocks we already know must have been there. Perhaps the most elegant counter-argument comes from the objects themselves. Could they be shepherding each other? Some simulations suggest that the collective gravity of the Kuiper Belt's known large objects, combined with the vast, unseen population of smaller ones, might generate enough of a gravitational tug to create the observed clustering through their own interactions. This idea of self-gravity turns the mystery inward, suggesting the pattern is not imposed from outside by a hidden master, but emerges organically from the complex dance of the swarm. It is a bottom-up explanation versus a top-down one, a democratic gravitational pull versus a monarch's decree. This vigorous debate is not a sign of weakness in the Planet 9 hypothesis. It is the sound of healthy science at work. Competing ideas are stress-tested, their predictions compared. The primordial disk theory, for instance, makes specific predictions about the types of orbits it can produce. The self-gravity model must account for the precise degree of clustering observed. Each alternative must survive the same rigorous scrutiny as the planet hypothesis. This back and forth is how we inch closer to truth, by pitting beautiful ideas against cold, hard data. The mystery of the clustered orbits remains, but the list of possible solutions reminds us that the universe is often more clever than our first guesses. The dark frontier holds its secrets close, and whether the answer is a planet, a disk, or a statistical mirage, the pursuit is reshaping our understanding of home. But the search for lost worlds is not confined to the dark outer reaches. It is also written in the sky above us every single night. Our own moon, that familiar silver companion, may be the most profound evidence for a ghost planet that no longer exists. This is the story of Theia, a Mars-sized world that lived and died in a single shattering instant, and in doing so gave Earth its greatest gift. The leading theory for the Moon's origin is the giant impact hypothesis, and it is a tale of cosmic violence on an almost unimaginable scale. Picture the early solar system, a chaotic construction zone filled with dozens of protoplanets jockeying for position. One of these, a world roughly the size of Mars, formed in an orbit eerily similar to Earth's. Astronomers named this lost world Theia, after the Titan goddess who was the mother of Selene, the Moon. For millions of years, Theia and the proto-Earth circled the Sun in a precarious harmony. But gravitational interactions slowly destabilized their dance, pulling Theia into a fateful crossing. About 4.5 billion years ago, the two worlds met. This was not a gentle merger, it was a head-on catastrophic collision. Theia struck the young Earth at a glancing angle, traveling at tens of thousands of miles per hour. The impact was so violent it would have vaporized Theia's entire mantle and a significant portion of Earth's own crust, launching a colossal plume of molten rock and vaporized metal into space. For a brief, hellish moment, our planet was crowned with a searing ring of debris, a torus of destruction glowing with the heat of 1,000 suns. From that incandescent chaos, gravity began its work. Within perhaps just a century, the ejected material began to coalesce in orbit, clumping together into the molten sphere that would become our Moon. This explains so much. The Moon is strikingly dry and lacks volatile elements compared to Earth, because the intense heat of the impact boiled them away. Its iron core is surprisingly small, because the collision primarily mixed material from the mantles of both worlds, while the dense metallic cores of Theia and Earth merged into our planet's center. Computer simulations of this event are both beautiful and terrifying. They show the two differentiated worlds approaching, their surfaces distorting under tidal forces even before contact. The impact itself is a splash of molten fury, a jet of material being launched into orbit while the cores sink into a single spinning mass. Over time, the debris forms a disk, and then a single dominant clump emerges, sweeping up the rest. The resulting Earth is left spinning faster, its day perhaps only 5 hours long and tilted on its axis, giving us our seasons. The evidence is not just in the Moon, but in us. The isotopic fingerprints of certain elements on the Moon, like oxygen and tungsten, are virtually identical to those on Earth, suggesting they came from the same source material. The Moon is not a captured stranger, it is our sibling, born from the ashes of a planetary twin that sacrificed its existence to forge our world. Theia is gone, but its legacy is the gentle light that guides our nights and stabilizes our planet's wobble. In a very real sense, we are looking at a ghost every time we gaze at the full moon, seeing the scattered remains of the world that made us whole. The collision that birthed the Moon was so violent it should have erased Theia completely, blending its material seamlessly into the young Earth. But what if fragments of that lost world survived? Deep within our planet, two colossal and mysterious structures might be the ghostly tomb of a planet. Seismologists mapping Earth's interior have long known about these anomalies. They are called large low shear velocity provinces, or LLSVPS, but you can think of them as two continent-sized blobs of unusually dense rock, each one larger than the Moon, anchored deep in the mantle near the Earth's core. One sits beneath Africa, the other beneath the Pacific Ocean. They are not part of the regular mantle flow. They are like ancient sunken continents resting on the core mantle boundary, nearly 2,000 miles beneath our feet. We know they are there because of seismic tomography, a process similar to a CT scan of the planet. When an earthquake occurs, it sends shock waves rippling through the Earth. Sensitive instruments around the globe measure the speed of these waves. They travel slower through hot or less dense material and faster through cold, dense rock. By analyzing thousands of quakes, scientists can build a three-dimensional map of Earth's interior. The LLSVPS show up as massive, distinct regions where seismic waves slow down dramatically, indicating they are made of something different, something denser and perhaps chemically distinct from the surrounding mantle. For decades, their origin was a profound puzzle. Were they piles of ancient, subducted ocean crust that sank over billions of years? Or were they primordial leftovers from Earth's formation that never mixed into the mantle? Then a radical idea emerged from the shadow of Theia. Could these blobs be the sunken remains of the impactor itself? In this theory, Theia's dense, iron-rich mantle did not vaporize entirely. A significant portion of it, perhaps the size of a small planet's core, survived the impact in solid chunks. These fragments, heavier than Earth's own mantle rock, would have sunk like stones through a molten sea, settling at the very bottom of the mantle, where they have remained for 4.5 billion years. Computer simulations show this is physically possible. The impacting world's mantle material could indeed survive and descend to form stable, long-lived piles. If true, these structures are not just geological curiosities. They are the largest relics of a lost planet, entombed within our own. The implications are staggering. These blobs are not passive. They actively influence our world. Their immense heat and different composition are thought to drive mantle plumes, which fuel volcanic hotspots like Iceland and Hawaii. They may even affect the behavior of Earth's magnetic field by altering the heat flow at the core boundary, so the story of Theia may not end with a splash and a new moon. It might be a story of burial and persistence, where the ghost of a lost world still stirs in the deep, shaping the geology and the very life of the planet it helped create. The quest for missing worlds is not a modern obsession. Long before we mapped the outer darkness, astronomers peered at our closest companion and saw, or thought they saw, another. In 1846, French astronomer Frédéric Petit announced a stunning discovery. He claimed to have observed a second moon of Earth, a tiny body orbiting our planet every 2 hours and 45 minutes. He even calculated its orbit, suggesting it passed so close that its gravitational pull could explain minor irregularities in the moon's motion. The scientific community was skeptical, and repeated observations failed to confirm its existence. Yet the idea persisted in popular imagination, a celestial phantom that refused to die. Decades later, in 1898, a German astronomer named Georg Waltemath went further. He predicted not just a second moon, but an entire system of them, including a primary body he named Lilith, after Adam's mythical first wife in some folklore. He described it as a dim, ashen-gray companion, visible only at certain times. Newspapers eagerly reported on these dark moons, but like Petit's claim, they vanished under the scrutiny of better telescopes. These were not hoaxes, but sincere errors, glimpses of asteroids or even high-altitude clouds misinterpreted by hopeful observers. They reveal a powerful human tendency to fill perceived gaps, to balance the cosmic books with unseen companions. This impulse stretches back to the ancient Greeks. The philosopher Philolaus proposed a wild idea to explain why lunar eclipses could sometimes occur when both the sun and the known moon were visible in the sky. His solution was a counter-Earth, which he called Antichthon. This was a hidden twin planet to our own, orbiting on the opposite side of a central cosmic fire, forever concealed from our view by the body of the sun. It was a beautiful, symmetrical answer to a flawed observation, a testament to the power of logical deduction untethered from evidence. While we now understand the mechanics of eclipses perfectly, the romance of a hidden twin world, a planetary doppelganger sharing our orbit, has never fully faded from science fiction. These historical curiosities are more than just footnotes. They are a mirror to our own search for Planet 9 or the remnants of Theia. They show that the drive to find what is missing is a constant in our study of the heavens, a blend of rigorous mathematics and boundless imagination. Sometimes, as with Neptune, the math leads to a real world. Other times it leads to a phantom, a Lilith or an Antichthon, born from a tiny error or a longing for symmetry. Each failed hypothesis, however, sharpens the tools of science, teaching us to distinguish the signal of a true mystery from the noise of our own expectations. The ghosts we chase tell us as much about ourselves as they do about the cosmos. Our own solar system's history is a story of chaos and lost worlds, but we are not unique. The telescope's eye, turned outward, reveals that this drama is playing out across the galaxy. Around young stars, we see the birthplaces of planets not as smooth disks of dust, but as rings divided by dark bands, like grooves on a cosmic record. These are protoplanetary and debris disks, and their gaps are the signatures of unseen architects. Using immense radio telescope arrays like the Atacama Large Millimeter Array, or ALMA, astronomers capture stunningly detailed images of these distant nurseries. We see brilliant rings of icy and rocky debris, glowing with the faint heat of formation, separated by stark, empty lanes. The most compelling explanation is that a young, forming planet is orbiting within that dark gap. As it circles its star, its gravity acts like a cosmic plow, clearing its path of smaller material, sweeping up dust and gas, and leaving a clean highway in the disk. It is a detective story written in light and shadow, where the absence of material is the clearest clue to a hidden presence. This method of detection, finding planets by the gaps they carve, complements other techniques like the transit method, where a world dims its star as it passes, or the radial velocity method, where a star wobbles from a planet's tug. But the gap method is special. It allows us to see the gravitational influence of planets that are otherwise too faint or too far from their star to spot directly. It reveals the systems in their youth, caught in the act of construction, and what we see is not always orderly. Some disks show wildly eccentric rings or gaps that are offset and warped, hinting at not one, but multiple planets engaged in a gravitational tug of war, scattering material and each other. This is where the concept of planetary migration, so crucial to our own solar system's story, is vividly confirmed. Young, massive planets can spiral inward toward their star, or be flung outward, their journeys carving chaotic paths through the primordial disk. In this turbulent environment, planet loss is not a catastrophe, it is a common outcome. A world might be ejected entirely, sent drifting into the interstellar void as a rogue planet. Another might be dragged into its star and consumed. The gaps and warps we see are frozen moments in this dynamic and often violent process. The implication is profound. Planet formation is a messy, unstable business. For every stable system like our own, there may be countless others where giants were lost, where terrestrial worlds collided, or where entire planets were banished to the dark. Studying these distant disks is like having a time machine. We are watching the early history of our own solar system play out around other stars, seeing the possible fates that Theia or a hypothetical Planet 9 might have shared. It suggests that our solar system, with its asteroid belt, its peculiar outer orbits, and its giant impact that formed the Moon, is not an oddity. It is a standard chapter in the galactic story of creation and destruction. The silent, dark gaps in those glowing rings tell us that what is missing can be just as important as what remains. They are a reminder that the cosmos is not a static museum, but a continuous construction site, filled with both the birth of new worlds and the ghosts of those that did not survive. These distant cosmic construction sites reveal a fundamental truth. Planet formation is a violent and unstable business. For every world that finds a stable orbit, another may be lost, cast out into the eternal dark. The mechanisms of planetary disappearance are as dramatic as they are destructive. One of the most common is planet-planet scattering. In a young, crowded system, massive worlds engage in a gravitational tug of war. As they jostle for position, their orbits can cross, leading to a close encounter. In this high-stakes dance, one planet might be flung inward toward the star, but another can be catapulted outward at tremendous speed, breaking free of its star's gravity entirely. This ejected world becomes a rogue planet, a dark, frozen nomad drifting alone through interstellar space. Simulations of this process are mesmerizing chaos. You watch as colorful orbs representing gas giants move in once stable rings, then one orbit stretches, becomes a slingshot, and a single world is hurled off the screen into the black, destined to wander the galaxy forever, never feeling the warmth of a sun again. Stellar flybys present another catastrophic scenario. Our sun now orbits in a relatively quiet neighborhood, but in its youth it was part of a dense stellar cluster. Close passes from other stars were far more common. Imagine another sun, perhaps a sibling from the same nursery, gliding a little too close to our early solar system. Its gravity would be an invasive tremor, reaching into the delicate orbital architecture. It could destabilize the outer planets, pulling one into a wildly eccentric path or even plucking it from our sun's grasp entirely, stealing it away to become a captive of the passing star or setting it adrift. Such an event could explain extreme orbits in our own system, or the complete absence of a world where one should be. The passing star acts like a cosmic thief, reaching into a planetary system and taking what it pleases, leaving behind only gravitational scars. Then there is the most final fate of all, tidal disruption. This is not an ejection, but a complete demolition. If a planet, perhaps already sent on a chaotic path by scattering, ventures too close to its star, or more terrifyingly, a black hole, it meets a gruesome end. The gravitational pull on the side of the planet nearest the massive object is vastly stronger than the pull on the far side. This difference, the tidal force, stretches the world like taffy. For a star, a close orbiting gas giant can have its atmosphere stripped away, leaving a bare core, but near a black hole, the forces are unimaginable. The planet would be stretched into a long, thin stream of superheated plasma, a process called spaghettification, before its remains spiral into the accretion disk and vanish from the universe. It is a total and utter erasure. These are the cosmic forces that silence worlds, the gravitational mechanics of loss that ensure our night sky is not infinitely crowded, and that the history of any system is written as much by absence as by presence. The most profound loss is not a world hidden in the dark, but one that has left the light behind entirely. Drifting in the abyss between stars are rogue planets, the ultimate lost worlds. These are not bound to any sun. They are cosmic orphans, condemned to an eternal, frozen journey through the interstellar void. Their story begins in the same violent processes we have seen closer to home. A young planet caught in a gravitational slingshot during a chaotic dance with its siblings can be flung from its system with such force it escapes its star's grasp forever. Alternatively, some may form alone, directly from the collapse of a small, isolated cloud of gas and dust, a star that never quite ignited, leaving behind only a dark, gaseous globe. Once free, their fate is sealed. Without a sun to warm them, their surfaces, if they have surfaces, plunge to temperatures near absolute zero. Any atmospheres they possess freeze solid, falling as strange, metallic snow onto landscapes of perpetual ice. Imagine standing on such a world. The sky is not black, but a profound, star-studded velvet, with no central light to cast shadows or define a day. The only warmth comes from the feeble heat of radioactive decay in its core, and perhaps the faint glow of tidal forces if it has a moon. It is a silence and a cold beyond human comprehension. Finding these dark wanderers is one of astronomy's greatest challenges. Since they emit almost no light, we cannot see them directly. Instead, we detect them by the subtle warping of spacetime they cause. This method is called gravitational microlensing. When a rogue planet passes almost perfectly in line between us and a distant background star, its gravity acts as a lens, bending and magnifying the starlight for a brief period, perhaps only a few hours or days. Astronomers see the background star temporarily brighten in a specific, symmetric pattern, a signature that betrays the invisible planet's mass and passage. Each such event is a fleeting glimpse of a ghost, From the number of these events observed, scientists estimate there could be billions, perhaps even trillions, of rogue planets in our galaxy alone, outnumbering stars by a staggering margin. The Milky Way may be filled with more lost, wandering worlds than those anchored to a sun. This raises a haunting possibility for our own solar system. Could we have lost a giant to this same exile? The hypothetical planet 9, if it exists on its extreme orbit, is still gravitationally bound, however loosely. But what if, in a more violent past, there was a true fifth giant, a sibling of Jupiter and Saturn, that did not survive the early gravitational turmoil? Simulations show it is entirely plausible. Such a world could have been ejected entirely, becoming a rogue planet billions of years ago. That lost giant would now be somewhere in the galactic dark, a frozen relic of our system's most chaotic hour, carrying with it the chemical signature of our sun's birth cloud. We may never find that specific exile, but its potential existence reminds us that our familiar planetary family is a snapshot of survivors. For every world that found a stable orbit, countless others may have been cast adrift, becoming permanent nomads in the great ocean between the stars. Their silent journey is the final, lonely chapter in the story of planetary loss. The rogue planets drifting between stars represent one kind of dark exile, but there is another, far more extreme possibility hiding in that same outer dark. What if the mysterious mass shepherding those distant orbits is not a planet at all, but a fragment of creation itself? This is the most exotic frontier in the hunt for Planet 9, the hypothesis that the gravitational signature belongs to a primordial black hole. Unlike the stellar mass black holes formed from collapsing stars, a primordial black hole is a relic of the universe's first violent second. In the intense, uneven density of the Big Bang, pockets of matter may have collapsed directly into black holes of almost any size, some as small as an asteroid yet containing the mass of a planet. One of these ancient frozen pinpricks could have been captured by the sun's gravity in the distant past, settling into that same extreme, tilted orbit that Planet 9 is predicted to occupy. The thought is staggering. A black hole, an object of infinite density, could be orbiting in our own solar system, a silent, dark knot in the fabric of spacetime just a few hundred astronomical units away. Detecting such an object would be a challenge unlike any other. It would not reflect sunlight or glow with infrared heat. Instead, astronomers would look for secondary effects, tiny bursts of light from the void. As the black hole moves through the sparse outer solar system, it would occasionally intercept a small comet or cloud of dust. The incredible gravity would shred this material, heating it into a brilliant, short-lived flare of X-rays as it spirals into the accretion disk, a single match struck in an endless night. Alternatively, its immense gravity could be spotted through microlensing, momentarily magnifying the light of a background star in a specific, telltale way. Searches for these faint, transient signals are already underway, sifting through decades of archival data from X-ray telescopes and planning new surveys. The implications rewrite our understanding of home. A primordial black hole in our outer solar system would be a direct sample of the universe's birth, a fossil from before the first stars ignited. Its presence would suggest that such objects could be common, perhaps making up a portion of the dark matter that binds galaxies together. Our cosmic neighborhood would harbor not just planets and ice, but a genuine singularity, a gateway to realms of physics we can scarcely comprehend. This idea pushes the mystery from planetary science into the realm of cosmology. Whether the hidden shepherd is a captured super-Earth or a primordial black hole, the pursuit forces us to confront the sheer strangeness that might be lurking in the shadows of our own star. The search continues not just for a missing world, but for a key to the universe's deepest secrets. This gravitational search for a missing world is not confined to science. It has already colonized our imagination. Long before astronomers plotted the orbit of Planet 9, storytellers were populating the sky with ghosts. Look to the oldest of sky traditions, astrology. For centuries, some astrologers have spoken of the phantom planet Phaeton, named for the son of the sun god in Greek myth, who lost control of his father's chariot and crashed. In this lore, Phaeton is a destroyed world, its remnants forming the asteroid belt, a celestial allegory for hubris and catastrophe that eerily mirrors early scientific theories. This idea gave the asteroid belt a story, a tragic past that made the cold mathematics feel human. That instinct to narrate the void explodes across science fiction. Think of the most famous lost planet of all, Krypton. Its destruction is not just a plot device to bring us Superman. It is a foundational myth of a more advanced civilization meeting a violent geological end, a warning etched in glowing green crystal. Or consider Alderaan in Star Wars. Its obliteration by the Death Star is the moment the Galactic Empire's evil becomes visceral, translating planetary-scale loss into a single, silent scream felt across the audience. These are not background details, they are emotional anchors. The entire premise of the classic series Space, 1999, hinges on a lunar catastrophe, the moon itself torn from orbit by the explosion of a fictional planet's waste dump, sending a human colony hurtling uncontrollably into the cosmos. The show is literally built on the idea of a lost world's aftermath. These stories resonate because they tap into a deep, primal fascination. A destroyed planet is the ultimate stakes, the most profound scale of tragedy and mystery possible. It speaks to our fear of existential fragility, our own Earth's vulnerability, while also thrilling us with the romance of rediscovery. What secrets died with that world? What lost technologies or forgotten histories might lie among its fragments? Every tale of a missing planet is a detective story set against the infinite. Science gives us the equations and the orbital anomalies, but culture gives those dry facts meaning, wrapping them in narratives of heroism, hubris, and hope. We look at the asteroid belt and see not just rocks, but the ghost of Phaeton. We hypothesize Planet 9 and imagine a frozen super-Earth with continents of alien ice. The line between the scientific hunt and the mythical one has always been blurred, because both are driven by the same compelling question: what else is out there, waiting in the dark to be found? This search for ghosts is far more than a cosmic treasure hunt. It is a fundamental test of our ability to read the universe. Every prediction, from the mathematical gap that revealed Ceres to the orbital clustering hinting at Planet 9, represents a profound act of faith in the laws of physics. When we find a missing world, we are not just adding a dot to a map. We are confirming that our understanding of gravity and motion is correct on the grandest scales. A confirmed Planet 9 would be a staggering triumph of predictive astronomy, rivaling the discovery of Neptune. It would prove that we can infer the existence of a major world not from a direct glimmer of light, but from the subtle gravitational whispers it leaves on smaller, distant bodies. That confirmation would instantly validate entire models of planetary formation and migration, showing us how giant worlds can be flung to the solar system's frozen fringe, reshaping our entire narrative of how our neighborhood came to be. The impact of finding such a world would ripple across astronomy. Its very composition, whether a captured exoplanet or a native super-Earth, would serve as a time capsule. By analyzing its reflected light, we could learn about the chemical ingredients present in the outer solar system's primordial disk, or even sample material from another star system entirely. It would be a new class of planet to study up close, offering insights into the most common types of worlds in our galaxy that, until now, have been missing from our own cosmic backyard. The search itself is a powerful engine for innovation. The need to detect a faint, slow-moving object in an ocean of darkness pushes telescope technology to its limits. It drives the development of wider field cameras, more sensitive infrared detectors, and sophisticated algorithms capable of sifting through petabytes of data to find that one anomalous pixel. The tools we build to hunt for lost planets become the same tools that discover distant galaxies, map dark matter, and find asteroids that might one day threaten Earth. Closer to home, the story of Theia is not just ancient history, it is the key to our own existence. Understanding that catastrophic collision explains why Earth has such a large, stabilizing moon, a feature that may be rare among rocky planets. Our moon's gravity steadies Earth's axial tilt, preventing wild climate swings that could have made complex life impossible. It drives the tides, which may have nurtured the very beginnings of biology in shallow, churning pools. By piecing together Theia's story from the moon's geology and the strange blobs deep within our planet, we are learning why our world is a living, temperate oasis instead of a barren rock. This knowledge helps us interpret the conditions on exoplanets, guiding the search for other life-bearing worlds in the cosmos. Ultimately, this enduring quest reminds us of a simple, humbling truth. Our solar system's story is not a finished book sitting on a shelf. It is a living document, with new paragraphs being written with every discovery and every answered question that leads to 10 more. The empty spaces on our maps are not errors, they are invitations. They call us to look deeper, to think more creatively, and to remember that we are part of a dynamic, evolving system that still holds profound secrets. Whether the answer is a frozen giant, a primordial black hole, or something we have not yet dreamed of, the search itself expands our understanding of home and our place within the vast, unfolding story of the universe. The final proof will not be a photograph, but a pattern of motion. Over the next decade, the Vera C. Rubin Observatory will transform our view of the solar system's dark frontier. Its legacy survey of space and time is designed to be the ultimate detective, capturing the entire southern sky in exquisite detail every few nights for 10 years. This relentless, all-seeing eye will create a time-lapse movie of the cosmos, and within that movie, any slow-moving object will be caught. If Planet 9 is where the math suggests, the survey will find it. The process will be one of elimination, watching for that single, faint dot that shifts position against the fixed stars over weeks and months, a telltale crawl across the immense celestial backdrop. This discovery would be a moment of pure scientific poetry, a hidden world revealed not by a lucky glance, but by a systematic, patient census of the night. It would be a triumph of prediction over chance, but what if the telescope sees nothing? A null result from such a powerful survey would be just as revolutionary. It would force us to abandon the planet hypothesis and confront the alternatives with new urgency. Is the orbital clustering a grand statistical fluke, a trick of our limited past observations, or does it point to something even stranger, like the collective gravity of a yet unseen primordial disk? A non-discovery would close one door while swinging open several others, pushing theorists to refine their models of the solar system's early architecture. The search itself recalibrates our understanding, regardless of the outcome. Beyond remote observation, the dream of a direct mission lingers. Sending a spacecraft to this hypothetical world is a staggering engineering challenge. Even at its closest predicted approach, Planet 9 is over 10 times farther from the Sun than Pluto. A probe using current technology would take decades to reach it. Yet mission concepts exist, often involving nuclear propulsion or sophisticated gravity assists. Such a journey would be the ultimate voyage of exploration, a multi-generational endeavor to visit a world that has spent the entirety of human history in profound isolation. The data returned would be priceless, a first-hand analysis of a primordial giant that could tell us whether it is a captured alien or a native exile. Confirmation would instantly rewrite textbooks and ignite a new golden age of planetary science. We would have a new class of world to study, a frozen laboratory for understanding planetary formation at the edge of a star's influence. Refutation would deepen the mystery of the clustered orbits, challenging us to find more elegant gravitational explanations. Both paths lead forward. This ongoing quest, this patient sifting of darkness for a gravitational whisper, embodies the very spirit of discovery. We are poised on the edge of knowing, our maps incomplete, our story still being written. The next chapter of our solar system's history is waiting in the data streams of a new telescope, in the silent drift of distant ice, and in the relentless human curiosity that compels us to search the shadows for light. From a simple mathematical pattern to a hypothetical giant in the dark, the hunt for lost worlds is the story of astronomy itself. It is a history written in gaps and anomalies, in the stubborn spaces where our maps said something should be, but our telescopes saw nothing. Each empty spot became a question, and each question launched a search that reshaped our cosmic self-portrait. The Titius Bode law pointed to a gap that yielded not one planet, but an entire belt of fragments. The wobble of Mercury conjured the phantom Vulcan, a ghost whose vanishing act helped reveal the curvature of spacetime itself. The hunt for Planet X gave us Pluto, a world that forced us to redefine what a planet even is. And now the clustered orbits of distant ice whisper of a hidden shepherd, a gravitational echo that may be a frozen super-Earth or something far stranger. These are not failures of observation, they are its engine. The idea of a lost planet does more than fill a blank on a chart, it challenges the completeness of our understanding. It pushes scientists to build better telescopes, to write more elegant equations, to imagine possibilities beyond the familiar. It reminds us that our solar system is not a static museum exhibit, but a dynamic, evolving system with a violent past and a hidden present. This journey from prediction to discovery and sometimes to disillusionment is how science grows. It is how we move from seeing a fixed set of lights in the sky to understanding a narrative of collision, exile, and enduring mystery. So the next time you look up at the night sky, remember that the story is still being written. Follow the new data from the great observatories. Watch as the digital sky surveys process their nightly harvest of light. The greatest discoveries are often not the answers we expect, but the new questions we learn to ask. Which of these lost worlds captures your imagination the most? Is it the tragic beauty of Theia, whose collision gave us our moon, or the profound isolation of a potential Planet 9, a frozen giant watching from an unimaginable distance? Let us know in the comments and keep looking up. The next missing piece is waiting to be found.